Welcome to lecture 19 in our class on stochastic processes. The topic of today will be the construction of the stochastic integral, as we had announced previously. We will instruct it in a pretty abstract fashion, and you might still at the end of this lecture not quite realize what this thing has to do with the problem that we discussed at the beginning of this chapter, namely, for instance, this integral that appears when we want to evaluate the total gains or losses which are realized by pursuing a certain investment strategy. So this very concrete representation of the integral will not yet be visible at the end of this lecture, but we will connect this abstract construction, which we will present today, to the more concrete and more tangible interpretation in the lecture number 20. So let us show now how we can construct an object which then will be the integral in the end, and it will, as I had just said a couple of times, crucially depend on the possibility to use the quadratic variation of a continuous martingale. Before we were discussing the construction of the quadratic variation for a continuous martingale which was bounded. That was our previous main result, or the only actual result of the previous lecture. And the first step today will be to generalize this construction to the case when the martingale is not necessarily bounded, and even more so when this process of which we want to get the quadratic variation is what we shall later call a local martingale, which is even a broader class of stochastic processes which have the property of a martingale only after appropriate regularization. Now, in definition of what we call a local martingale. That's now the broadest class of almost martingales that we want to deal with, and which can serve as an integrator, so as that quantity or that process whose infinitesimal increments shall serve as an integrator for other processes. So MT, let that be a continuous process. And recall that we wanted to call a process continuous when almost surely it has continuous paths. Then this process on a filtered probability space, which has a filtration which is indexed by continuous time, is called a local martingale. If we find an increasing sequence of stopping times, which are stopping times with respect to the filtration which we were starting with, or at least with respect to the filtration which is generated by the process M itself. So we want to have a sequence of stopping times which are increasing and which for each omega tend to infinity almost surely, such that the corresponding sequence of stopped processes for any k, which is one of those fixed stopping times, is a martingale. If we find such a sequence of stopping times which increase to infinity almost surely, pointwise, and which have the property that if we stop the process, this M process, by means of the stopping time tau k for each index k, if that resulting process will be a martingale, a conventional martingale, then the initial process is called a local martingale. So this is what we shall understand as a local martingale. It's a martingale if we regularize it by means of stopping times. And if we find such a regularization, in order to have at each level of regularization a martingale, then we call the process a local martingale. Of course, every martingale alone is a local martingale. In fact, there you can just take deterministic times, which increase to infinity, for instance, or you just can take away the stopping time tau equals infinity right away, if you like. But I want to present to you an example of a martingale, correction of a local martingale, which is not a martingale. And it is a standard example, which you can, for instance, in Wikipedia, and which is constructed as follows. It is obtained by accelerating the trajectories of a Brownian motion. So let B be a standard Brownian motion. And then I want to construct a new process, MT, which is obtained by accelerating Brownian motion by means of a time transformation. So I run through the trajectories of Brownian motion with an accelerated time, which is this time transformation, which effectively produces an infinite speed or an infinite transformation of time when I approach with my time parameters to 1. So I rush through the Brownian trajectories faster and faster, but I want to freeze the Brownian trajectories, those accelerated trajectories, whenever, say, I hit the first time the level -1. So that's the definition of the process. I go through these trajectories infinitely fast with an acceleration, infinite acceleration towards the time point 1. And then I freeze the trajectory when I hit the level -1 for the first time. And by reflection principle, for instance, I know that this happens in finite time almost surely. So this time point t, this stopping time t, will appear in finite time almost surely. So therefore, even before I reach this level where the -1, so in other words, I reach the level -1 before I eventually need to follow a Brownian trajectory until, if you like, until time infinity. So therefore, the level -1 is reached in finite time, even before time equals 1. And by this mechanism, when I approach with the time parameter t here, the level 1, then by this construction, I can make sure that if t approaches 1, I will necessarily have stuck, or will have got stuck with the trajectories of the process at level -1. And then I just continue the process after this moment of time 1, which is the very latest, if you like, point that I can insert rigorously into this time-changed formula. Then after time point 1, I just continue all trajectories at the level exactly -1. So you see, I'm accelerating a Brownian motion for an explosion in finite time, but before the explosion actually happens, I will make a stop at the level -1. And then I claim that this process is a local martingale, but it is not a martingale. Well, we can see right away that this process mt cannot be a martingale, because if it was so, it had constant expected value. But bt is a Brownian motion that starts in 0, so at time equals 0, this process also is in 0. But at any time larger or equal than 1, the process is exactly -1. So the expected value of the process at any time larger or equal than 1 is -1, which cannot be if m is a martingale, because martingales in particular have constant expected value. But now I want to show that this at least is a local martingale. So in fact, we introduce now this sequence of stopping times, which will convert the process into a martingale if we stop with these stopping times tau k, and it is defined as the first time when this accelerated process exceeds the level k, say where k is a natural number. And so what's then the stop process? Well, the stop process, if I stop this m process with these stopping times, and note that these stopping times are formulated in terms of the m process, I can represent these trajectories of the m process as the accelerated trajectories of a Brownian motion, which is stopped either when it exceeds in absolute value the level k, or when it hits the level -1 for the first time. So in other words, through this application of the stopping time, the trajectories of the stop process can be represented as the accelerated trajectories of a Brownian motion, which is stopped either at the first time, which is stopped at the first time when it either exceeds in absolute value the level k, or when it first hits the level -1. Now, without this acceleration, the Brownian motion trajectories, which are stopped by this stopping time, would be a martingale, as we know, since this would be just a classical application of the optional stopping theorem. But in particular, this Brownian motion, this stopped Brownian motion, is a bounded martingale, so therefore it's closable in particular. And so therefore, this martingale has an has an infinite closure, and so therefore this construction or this representation of the stop process after this acceleration through the closure random variable of this martingale makes sense. And then it's an easy exercise to convince yourself that this effectively, after this time transformation, is in fact a martingale. So the critical point here is that the stopped M trajectories turn the martingale even in a closable martingale, and then this acceleration produces no harm. So therefore, for any level k, when I do this stopping, this stopped process is in fact a martingale. Moreover, these level times or these stopping times tau k, they are strictly diverging because, or they're strictly increasing because the condition becomes weaker and weaker until I will apply first the stopping, and I can convince myself easily that these stopping times converge to plus infinity for k to infinity. And hence I have just shown that this accelerated Brownian motion, which is stopped at the level -1, this accelerated Brownian motion is a local martingale, but not a martingale. So you see that this class of local martingales is not empty. It's this set of all possible processes with continuous paths for which, by whatever reason, we can find a sequence of stopping times such that the stopped processes are martingales, but the processes without any stopping are in fact not any martingale. And these stop processes, or these local martingales, appear at a lot of instances as long as you want to deal with kind of formal computations. And whenever you want to deal with processes and don't want to really talk about the integrability properties, then your first or maximal class of processes in which you want to work will always be the class, for instance, here of local martingales, which would allow you to do some computations on trajectories without really needing to bother too much about the integrability conditions, as long as you don't want to pass to the limit for this sequence of stopping times. So it's a very practical notion, and we will work with this class of local martingales a lot. And we have a criterion by which we can say that the local martingale is in fact a martingale, and this criterion is straightforward. It would be formulated as follows, for instance. So a local martingale is in fact a martingale if for all sequences of stopping times and any fixed non-negative time parameter t, we have that the collection of random variables which are obtained by evaluating this sequence of stopped martingales at fixed per terminal time t, and this is a uniformly integrable sequence of random variables. So that's as I said before, the question whether a local martingale is actually a martingale or not is in fact a question of uniform integrability. And this is highlighted again by this lemma, which tells you that if you have enough integrability, then a local martingale is also automatically a martingale. And I leave the proof of this statement as an exercise. Now we want to work with this class of local martingales, as I said before, because this will allow us to do all kinds of computations and in a way postpone the question about integrability of all these processes, which can appear to something that we do later, if you like, in each of such considerations. And what is very nice is that we can talk of a quadratic variation not only of bounded martingales, but also of the much bigger class and the much bigger class of local martingales. And the theorem, which is the terminal theorem about the existence of quadratic variation that we want to show in this class, is the following. So let M be in fact a local martingale now. Then there exists a unique process, which is again denoted through this bracket notation, MM, which is of continuous trajectories, which are non-decreasing all, which starts at 0, such that the square of this local martingale, upon subtraction of this process, of this bracket process, again is a local martingale. So it's exactly the same kind of statement that we had before in the previous lecture, which was dealing with bounded martingales, not only with not even with martingales with bounded martingales, but here we have a much wider class of processes on which we apply this, And here the statement is that even for local martingales, we have this unique compensator process, which is the bracket. And also we have this possibility to approximate the bracket by discretized quadratic variations, namely for all possible sequences of partitions of the non-negative time axis, which whose mesh converges to 0. We have that for k tending to infinity, and for all positive maximal time parameter, we have that the supremum of these discretized quadratic variation process, when evaluated along the grid delta k, such that the possibility or the probability of a deviation of this discretized quadratic variation from the actual bracket process being greater than epsilon when evaluated uniformly on the interval from 0 to L, then this will converge to 0. So this convergence here that we apply here, or this convergence that we're talking about here, is also called the convergence locally uniformly in time in probability. So I could phrase this last statement in words as follows. The quadratic variation process, or the bracket process of a local martingale, appears as the locally uniform in time, limit in probability of this sequence of processes which are obtained by discretized quadratic variation approximation along a sequence of grids on the non-negative time axis, provided that the mesh size or the maximal step size of these grids converges to 0. So this statement says that we have a notion of quadratic variation which is quite uniquely determined through these compensating properties for local martingales. And the proof of this depends on the possibility to define this bracket process to start with, and it depends therefore on the following lemma, namely if M is, say, for instance, a bounded continuous martingale, so a martingale whose values are all insert a certain corridor, not too far away from the origin, and if we have a stopping time which is finite, then we can consider the quadratic variation process of the stopped martingale, which again is of course a bounded martingale, and we can evaluate it at any time. And we can also take the bracket process of the non-stopped martingale. We can stop the bracket process and evaluate this at any time. And the statement is that these two things are the same. So it says, taking the square increments of a process and stopping the square increment process, if you like, the measurement of the square increments after a certain time is just as good as if you stop the process first and then add all the square increment processes. Square all the increments of this stop process. Why is that plausible, this statement? Well, it said in both cases you just freeze either you freeze the quantity which you want to observe, which is these increasing numbers of quadratic jumps or quadratic increments. That's on the right-hand side here. Or you just freeze the trajectories of the process of the left-hand side, so that after this freezing time, you observe no more change in value of the trajectories, and therefore, of course, the quadratic variation will no further grow after the freezing has occurred. So this statement is absolutely plausible, if you think about it, what it actually means, and the proof goes as follows. It goes through this unique characterization of the bracket process as the unique non-negative, the unique continuous non-decreasing process which compensates. And therefore it's an application of optimal stopping. So let's consider the stopped process, which is, since M was a lone bounded martingale, this is also then a bounded martingale, and so we have the notion of a quadratic variation, and it's basically uniquely determined by this property that if you subtract the square, then you get a martingale, or you subtract that thing from the square of the process to get a martingale again. And also we have, of course, the same property for the unstopped quantities, namely the unstopped process squared and subtracted from that the bracket process, this is a martingale again. Now, if we subject the letter process to stopping, of course, by optional stopping, we get a martingale too. But what does it mean to take this? Well, if you take the stopped process, which is the sum of two processes, or the difference, then this is nothing but taking the stopped processes alone and take the difference of that. So this is what we have here. But of course, the square of the stopped process is the same as stopping the process and squaring it. So therefore, we see that also the stopped process squared minus the stopped bracket process is a martingale. And if we compare this line with this line, we see that two possibly different processes, namely this one and this one, both are compensators for this stopped martingale. They are both non-decreasing, start in 0, and both are continuous. So they must be the same by the unique characterization of the compensator, which is the lemma. With this, we want to show now that we have this quadratic variation process also for local martingales. So therefore, let us start with a local martingale. And by definition of a local martingale, we know that there is a sequence of stopping times which are increased to infinity, pointwise almost surely, such that for each of those stopped processes, that leads to a martingale. We want to apply the previous theorem from previous session about bounded martingales. So let's make sure that we talk about bounded martingales, and this can be done by applying yet another stopping to this already stopped process, which is that we stop even further. So we reduce the stopping time tau k by another stopping time of which is inserted as another infimum. Namely, we want to take the stopping time tau k prime, which is the infimum of the old tau k, and the first time when the martingale or the local martingale exceeds a level k. This means that if we stop the process m by this new stopping time tau k prime, which is even below tau k, then by definition the trajectories of these processes are all lying in the corridor of values which are no further away than k from the origin. So in particular, this process is a bounded local martingale, and if you like, even closable, but that's not so important. Okay, but for bounded local martingales, in the previous session, in the previous lecture, we have seen that the quadratic variation process exists. And it is obtained, for instance, as this limit in probability of this sequence of approximate quadratic variation processes. Moreover, we know that this sequence of stopping times tau k prime is also increasing, and in fact increasing to infinity. So we can apply the previous lemma to the process tau, which is stopped at stopping time tau k plus 1, tau k plus 1 prime, namely this stopped martingale, a local martingale with the stopping time tau k plus 1 prime, stopped with if you take the bracket process of this and we stop the bracket process of this, this is by the previous lemma the same as if we had applied the stopping to the process of which we want to compute the bracket and evaluate the bracket process there. But if we stop the stopped martingale, which was stopped at the later stopping time, and we stop it now even one step further, this is of course the same as just applying the stopping time tau k, so the smallest stopping time immediately. And what do we see? We see that the bracket process that belongs to the martingale, which is obtained from the local martingale by a later stopping, when we restrict this to the interval, which is up to the time tau k prime most, then we get the same trajectories as if we had computed the bracket of the martingale which is obtained by stopping earlier. So this is expressed in this line. It says that the bracket process for the next level stop martingale restricted to those times which are prior or at most before the stopping of the martingale the step before, then this is just the same as the bracket process for the corresponding previously stopped martingale. Which means that we have a consistent sequence of processes. We have larger and larger time intervals which correspond to these expanding periods of time before the first stopping appears. And on each of these intervals we have we can understand that all these bracket processes for the martingales which are obtained by stopping later, that all these bracket processes on these subintervals are the same. So therefore we can define in a well-defined fashion the trajectories or a certain process which we call the bracket process of this local martingale. We can define it as the pointwise limit of the bracket process of the sequence of stopped martingales. Let me say it again. So this, for the well-definedness of this quantity, we use that, if you like, we have increasing sequences of intervals, tau k prime, tau k plus 1, tau k plus 2 prime, and so forth. And on each of these, if you like, on each of these time intervals, we have a sequence of stochastic processes which that's not a very good picture, but anyway, we have a sequence of stochastic processes which coincide, which are just the same processes if we restrict that to each of these subintervals. Which means that if we fix a certain time t, and we want to define the value of this trajectory of this process or of a process at this fixed time t, we can pick any tau k prime big enough, which is bigger than the t, which eventually will happen because tau k is a sequence of stopping times which converges to infinity. And then we can pick any of those trajectories to define the value of this process at this moment of time. This is then our definition of a bracket process for this local martingale. And we will have to show that this bracket process satisfies the properties that are in the claim of the theorem. Okay, we want to show that this bracket process is the compensator. So in the claim it says that the bracket process is the compensator for this m squared process in order to obtain a local martingale. Okay, so the only thing we have to show is that we find a sequence of stopping times that this stop thing is a martingale for each of the levels of the stopping. And so it's canonical and natural to choose the stopping times tau k prime to start with. So we take this m squared process and the bracket process, which we had just defined, and we apply the stopping with level k, with these modified stopping times tau prime. Then, of course, the stopping of the square is just the square of the stopping. And then we have the stopped bracket process. And we know by the previous construction that the stopped bracket process is nothing but the bracket of the stopped process. And we had already seen, or that was just basically the definition of the bracket process for the stopped martingales, that this is in fact a martingale. So therefore we have convinced ourselves that this increasing process is in fact a compensator. It is the right process to subtract such that we find a sequence of stopping times such that this difference of these two processes for each level of stopping is a martingale. And also this MM process is obviously an increasing process, and it's a continuous compensator, and it's uniquely characterized by this, which follows exactly the same argument as in the case for a bounded martingale, because if you had two of such processes, then these two of these processes there would be a difference of two processes, would also be a martingale of these two guys, and it would be a martingale which is of bounded variation, and it would also be, yes, so it would be a martingale of bounded variation, and we have convinced ourselves already that a martingale of bounded variation, or even a local martingale of bounded variation, must be the zero process. So therefore it's unique. There can only be at most one of such processes. And finally, we want to show that this bracket process, also in the local martingale case, can be obtained as the limit in probability, which is obtained locally uniformly with respect to the time parameters. So therefore, suppose we have a partition of the real axis, non-negative real axis, and we want to consider this maximal deviation of the approximate quadratic variation or bracket process and its limit, which is the supposed limit. And we observe this, as said, on the time interval from 0 to L. We ask what's the probability for a deviation by more than epsilon. Well, then this probability can be decomposed in two parts. And here is a misprint. Namely, either the stopping time tau kl prime is less or equal to L. So I take the intersection of this event, or I decompose this event, which is described on the left-hand side. I intersect this event with the event that either the stopping time tau k prime, which is any of those stopping times, is less or equal to L. And then I have the complement, the local complement of this, which is in terms of probability and additivity of disjoint unions. Then this second part is the probability of that event, which I described to start with, intersected with the additional complementary condition that the stopping time tau k prime is greater or equal to L. Okay, and to be absolutely correct, I should probably write a strictly less here also. Okay. Well, in fact, I intersect what I did here obviously was I decomposed this event here into two sub-events, which are exactly this event intersected with these two complementary conditions, but in terms of an upper bound of this probability, the first of these two summands is simply bounded from above by the total complement probability of this here. Now, if tau k prime is a sequence of stopping times which converges to infinity almost surely, then for any given level L, I can find a large enough k such that the probability here is really very small. So the first of these two event probabilities can be made arbitrarily small by the convergence or divergence of the tau k prime stopping times towards infinity. So therefore this is a very small probability event if k is chosen sufficiently large. And as for the other event, if the stopping time tau k prime is larger than L, so if I evaluate only these trajectories in this case, then obviously the stopping that I might apply to the process M and also its bracket process will not be visible, will not have occurred yet on this time interval from 0 to L. So therefore, since all these are local and time constructions, it does not make a difference as long as I'm on this sub-event to replace this M process when the stopping hasn't yet really kicked in by the stop process, because these two trajectories don't differ. And so I can replace the process by its stop version. But for the stop version and fixed k, I know that this is a bounded martingale, and so therefore I have this convergence uniformly in time in probability, which tells me that if delta is sufficiently small, the second summand of this inequality will be small, sufficiently as small as I like, So in particular, the sum of the two things will be smaller than any delta, for instance, if, as I just said, the k index is chosen large enough such that this probability is less big than delta half. And if I have fixed the k index, then for that k index I can choose a mesh size, maximum mesh size less or equal than, strictly smaller than 1 or whatever, just small enough, such that the remaining probability is also less or equal than delta half, which in total shows this local in-time convergence and probability of this approximate quadratic variations to the bracket process. Okay, that's very good news now. Okay, we have this well-defined bracket process for any local martingale, and in particular we have now a famous first really significant result for actually our theory of Brownian motion. Namely, we can now say that the bracket process of Brownian trajectories is just a T process. And that's a remarkable result. I will explain it in a second why it's so remarkable, or probably you don't find it remarkable. I do. And why is it true? Well, okay, the process T as a process in time is non-decreasing continuous. It starts in 0, and we had already seen at one of the very first lectures on Brownian motion that if I take the square of Brownian motion and I subtract the identity in T as the T process, then this is a martingale. We had already seen that very early on when we talked about Brownian motion. So in particular, the T guy is the unique compensator. And of course, Brownian motion is not only a local martingale, it's a martingale. So as an application of this unique characterization, we know that the T guy, the T process, is the compensator for Brownian motion, which is a very specific property. And why is that so remarkable? Well, Brownian motion is a very rich and very, very random object, trajectory. And what this says is that nevertheless, what the trajectory is that we observe, the sum of the infinitesimal quadratic increments, when we sum all those infinitesimal quadratic increments up to a moment of time t, then the sum of these infinitesimal quadratic increments is t for all trajectories. So in a way, if you think about this as some sort of an energy, yeah? So the Brownian motions, they do go up and down, and their total energy is measured in the total amount of fluctuations, but in this quadratic fluctuation style, right? So then this says that in spite of the diversity of Brownian motions, trajectories, they all have the same energy, which is just a deterministic constant. And if you think of it like this, you probably find the result quite remarkable, that they are really very different, but the randomness is completely disappearing on the level of quadratic variation. By definition and by construction, the bracket process is a quadratic construction. It takes the increments of a given process and squares it. And so, for instance, if we introduce or insert lambda times the bracket times the process inside the bracket operation, we get the lambda squared as a prefactor outside. So it's a quadratic operation, and with quadratic operations you can typically do what is called a polarization in order to convert this into a bilinear operation, and that's what we do next for two local martingales m and n. We introduce the bracket of those two martingales as follows. It's 1/4 of the difference of the bracket of the sum of the two martingales m and n minus the difference of the bracket of m and n. Then this is, by definition, a difference process of two processes which are increasing and continuous. So therefore it is a process of bounded variation. And in fact, mn, here's another misprint, mn mn is the unique continuous process of bounded variation which starts in 0 such that if you take the pointwise product of two martingales, of these martingales m and n, and subtract this joint bracket, then this is again a local martingale. So this is in fact just the bilinear extension or the bilinear version of the previous results that we formulated for the case when m equals n. And similarly, we also can conclude that we have a locally uniform in time convergence and probability of a corresponding sequence of approximate quadratic covariation processes. So another name for this bracket m and n is the quadratic covariation process. So we have a discrete approximation of the quadratic covariation process, which is obtained by taking the products of the increments of the two factor local martingales m and n on these time grids, and by summing those products up. So that's just the corresponding bilinear extension of the previous construction of the bracket of a martingale with itself. Here we have the co-bracket, if you like, or the quadratic covariation, as it is also sometimes called. And this follows straight away from the corresponding situation when we have dealing with the situation that we have one martingale, and we can conclude all this for the bilinear case from the corresponding case of on the diagonal when m equals n, by keeping in mind this polarization identity, which, for instance, for the case of the product of two real numbers, is just the trivial statement that the product of a and b can also be expressed as 1/4 of a plus b squared minus a minus b squared. And this tells you that, in a way, everything you want to say about the product of two real numbers can be deduced from the squares of real numbers, if you use this polarization identity. So therefore, these statements here are directly deductible from the corresponding statements when a and b, in this case, are replaced by m and n, the two factor martingales. This, in conclusion, means that for two local martingales, we have what we call the quadratic covariation process, or just the bracket process. And note that the bracket of two martingales or local martingales is not necessarily an increasing process, but by definition or by construction, it is still a process of bounded variation because it's a difference of two increasing processes. The next important element in the construction of the stochastic integral is what we call the Hilbert space of square integrable martingales. Namely, given a filtered probability space where the filtration is indexed by continuous time, we can define the space curly h to be the collection of all martingales, which are martingales with respect to the filtration ft, such that they are bounded in L2 uniformly, in the sense that the supremum of all L2 norms of this martingale for a given M process, that the supremum of all these L2 norms of the martingale, as we let time range over all non-negative time indices, that this is finite. Well, of course, this supremum is just the limit for t tending to infinity, because by Jensen's inequality, mt squared is a submartingale, so hence these integral of the mt squared as a function in t are non-decreasing. But we want to introduce, nevertheless, this notation, namely, let's say again, h, curly h, is the collection of all martingales on a given filtered probability space in continuous time, whose L2 norm is uniformly bounded. Then we have the following proposition, namely, if m is in this space h, so m is a uniformly square integrable martingale or uniformly L2 bounded martingale, then this martingale is in particular closable. So therefore we have this closure random variable m infinity, which is in L2 then. That's the statement, that this closure is also an L2 variable. And this space curly h is in fact a Hilbert space, which we can equip with the norm that it's just the limit of these L2 norms. If we have one such process as the martingale, we just take the maximal occurring L2 norm of the random variables that constitute the martingale square. That would be the square. And likewise, or as a consequence of this definition, this maximal L2 norm can also be obtained by just taking this closure random variable m infinity of this closable martingale and take the L2 norm of that. And the claim here is that this is a Hilbert space and that these two expressions coincide. And we have an equivalent norm on this Hilbert space, which would just be the L2 norm of the maximal process evaluated at infinity. That's an equivalent norm. And we have an embedded subspace, which is the collection of all those square integrable martingales which start in 0. And in this case, we can also work with the norm, which is just the evaluation of the bracket process at infinity. Now recall that the bracket process is a process which has non-decreasing trajectory, so therefore trivially this m infinity random variable exists as a limit of as a limit in time of a non-decreasing sequence or non-decreasing process, and this norm, this expected value of the closure random variable in L2 is equivalently given as the bracket process, the expectation of the bracket process at infinity. Okay, let's prove this. Well, M is uniformly square integrable, so it has a uniform bound on the L2 norms, so therefore it is uniformly integrable. That was in fact an exercise or a problem on one of our problem sheets. So we have that this is uniformly integrable, this sequence of random variables, so therefore this, by Dup's convergence theorem, we have a limit, which is this closure random variable, and it is also this closure random variable is in L2, which is a consequence of Fatou theorem, which tells us that this m infinity squared in L2, or in the expectation of f n infinity, is less or equal than the limit inferior of the corresponding L2 norms of the random variables which converge pointwise to m infinity. And this is finite, so therefore m infinity is a square integrable random variable. And suppose now that we have a Cauchy sequence in this space H, where we equip the space H with this norm of the maximum of L2 norms, then we can apply it to this difference of two of those instances of the Cauchy sequence. So K is now the index for the sequence of martingales which are in this space H. So that as a difference of martingales is of course again a martingale, and we can apply to this difference, for instance, the Dupf maximal inequality, which tells us that the pathwise supremum of this difference up to a certain moment of time t, and again here's the misprint, is that this is given or is bounded from above by a certain constant times the actual value of these differences, in this case differences, at terminal time t, where t is this time interval on which we want to consider the pathwise supremum. And since this is Cauchy with k and l, these are, again, let me say it again, it's just the sequence parameter for the sequence. We're assuming that this is a zero sequence, or when k and l tends to infinity, this tends to 0, which means that we have a pathwise limit, which is then our candidate for the limit process in this H space. We want to show that this is in fact a space, an element in H space, which again follows from, for instance, Fatou lemma. And we also know by the definition of the norm of this space capital H, that the norm of this space of an element in this space capital H is by monotone convergence given by the L2 norm of the corresponding limit random variable. So since we were assuming that this sequence of martingales is Cauchy, this says that these infinite random variables are also converging in L2 space, in fact. And therefore we have a limit variable for this closure, for the sequence of closure random variables, and it's clear to say, or it's clearly to see, that this limit random variable is in fact the limit random variable or the closure of this Martingale MS. And in particular, again, by Dup's maximal inequality, we can see that this pathwise approximation is true towards this limiting random variable ms, m infinity, I'm sorry, where s here is the time parameter. And this all allows us to conclude that this limit random variable, or this limit process, in fact, is an element in H, and we have convergence in this H space. So this was obviously quite quick, but these are more or less standard arguments in Hilbert space theory about the completeness of Hilbert spaces. But here it is conducted in this Hilbert space of processes where the critical ingredient is, or the 2 or 3 critical ingredients for the argumentations here are either Fatou lemma or Dup's maximal inequality. Yeah, these are the 2 critical ingredients, and probably also the fact that you can work with the closure, or the closure variable of these random variables of these Martingales. Okay, what was the third statement again? All right, this third statement was that we have an equivalent norm on this space, which is just the L2 norm of the pathwise supremum. I want probably to skip over this because it's just a straightforward consequence, again, of the Dupe maximal inequality, which tells me that I can estimate the supremum of this super martingale, which is obtained by taking the square of the initial martingale by the expectation of the terminal of the value of the martingale at the terminal time, where the terminal time is the terminal time of the time interval on which I want to consider the random variables here, and this would then immediately give me an equivalence of these expressions, and then by sending the terminal time to infinity, I obtain the claim. And finally, if I have the subspace of square integrable martingales which start in 0, well, then this is by L2 convergence, is obviously a closed subset of this space of square integrable martingales. And if I compute, for instance, the expectation of this martingale squared of this martingale which starts in 0, then I can add and subtract, or I can add a 0 by adding and subtracting the bracket process. But the bracket process is the compensator for M, so therefore the first 2 parts here together constitute a martingale whose expectation is constant over time. So therefore the expectation of the first of the difference of the first 2 terms is the same as if I take the expectation of the first 2 terms at time equals 0, which by construction is a 0. So I find that the expectation of this martingale squared is the same as the expectation of the bracket process at time t, and then I can just, in this equality, by again monotone convergence, let tend t to infinity. Yeah, by dominated convergence, or here, let me say that here it's by dominated convergence. I can, and uniform integrability, in fact, I obtain the statement that the expectation of the closure random variable m infinity squared is the same as the expectation of the bracket process at infinity. Okay, so this was the introduction of this process H of square integrable continuous martingales, and that's a very convenient space because it's a Hilbert space. We have managed to construct a Hilbert space of stochastic processes, and we will use this Hilbert space of stochastic processes now in order to give a rigorous definition of the stochastic integral. We will make use of the Ries representation theorem in this Hilbert space. That will be our strategy now. So the Hilbert space curly H will be the space in which we will look for a candidate for what we will identify as the stochastic integral process, in fact. And what we need now is a description of the collection of processes which can be integrated. So the theory of stochastic integration has two components, if you like, or if you want to take a stochastic integral of something against something, then you need to define what is to be integrated, and you need to define what is the integrand. So if you think about the example of the investment strategy and the total wins or losses that come with a certain portfolio strategy, we had the integral of a theta process against the dB, against the increments of the Brownian motion. So here in that case, the Brownian motion is the integrand, and the theta process is the process which is to be integrated. And the next one or two concepts will specify what are appropriate processes that can be integrated against a martingale. Namely, a stochastic process X on a probability space is called a measurable process if, when we consider the process as a joint map which accepts a time parameter and a randomness parameter, omega, and spits out or gives back the value of the stochastic process at the time t for the given realization of randomness omega. If this map from the joint space of times and realizations of randomness into the reals is a measurable map when we consider it, as I just said, as a joint map of time and omega into the reals. So it's just saying that a process is measurable if and only if, as a map in two variables, namely time and omega, it's a measurable map, where naturally we equip the domain space with the product sigma field, which is obtained from the Borel sigma field on the non-negative real line, and the sigma field F, which is the probability space, is the sigma field on the probability space on which the process is defined. And we have a little proposition, which is a little exercise for the proof, is a little exercise in elementary measure theory, namely that a process X is measurable as such, as we just defined, if and only if we can find a sequence of step functions effectively. Step functions here, in this case in time, which approximate the given process X for all possible arguments t and omega. And the step functions that we want to consider are step functions which are piecewise constant in time, and each of these piecewise constant in time indicator functions is multiplied by a certain random variable, which is a random variable exclusively in omega. So in other words, it says that a stochastic process which is measurable can be approximated by basically indicator functions, where the indicator functions are indicator functions of rectangles. The rectangles are rectangles in the respective coordinates of a time interval on which the random variable is defined, and then, if you like, it's a piecewise constant random variable on each of these respective time points. So what you would call this is a step function, if you like, a step function in the time parameter. So let me say it again. A process is measurable if and only if we can find a sequence of pointwise approximations. So a stochastic process is measurable in the just defined sense if and only if we can find a sequence of piecewise constant functions which approximate the given process pointwise, where a piecewise constant function here is to be understood as a piecewise in time constant function. This statement follows from a monotone class theorem or simple measure theoretic induction. The only thing you have to keep in mind is that basically the Borel sigma field on this product space is induced from a rectangular sets which are Cartesian products of intervals or half-open intervals with respect to the non-negative real lines and certain indicator function or certain elementary set in the sigma field F. And if you realize that this sigma field which we describe here is generated by these simple rectangular sets, then this representation or the possibility to approximate a measurable function by such simple rectangular functions, stepwise constant rectangular functions, is a direct consequence. And if you want to do it in full mathematical rigor, you would use, for instance, the monotone class theorem or any other argument of measure theoretic induction to make it a rigorous proof. But I don't want to spend too much time on it because the mathematicians among you are surely fully aware of this technique to prove that. And for everyone else, it's not so important. And we want to define now properly the collection of those random variables, or to be precise, those stochastic processes, which can be integrated against, which can properly integrated against a given martingale. So we choose a square integrable martingale from the collection of H, so from the collection of all square integrable martingales. So that's a continuous square integral martingale. It's coming from this Hilbert space that we had just discussed. And we introduce now a set of stochastic processes which we will be able to integrate against this given martingale M. And this will be the so-called L2 of M space. So it's the space of all measurable processes in the sense that we have just discussed, whose L2 norm relative to the martingale M is finite. And what is the L2 norm of a measurable process relative to the square integrable martingale M? That's an important quantity which we shall introduce now. It's obtained by doing what? You take this x process squared, so you take the x process, which is a real valued stochastic process, measurable. You take the square of this. So we will now introduce a reasonable and proper subset or set of processes x which can be integrated with respect to a given continuous martingale, in this case, which is taken from this set of square integrable martingales curly h. Namely, given a probability space which is filtered with the filtration indexed by continuous non-negative time, and let M be such a process from the square integrable martingales with respect to that filtration on that probability space, then we can introduce the class of square integrable processes with respect to the given process M. And this is defined as the collection of all those measurable processes, where measurable is to be understood as in the sense that, as we discussed before, which are square integrable with respect to this given martingale M as follows, namely this norm or this quantity x of the process, which is written as a norm with regards to the given martingale M, is defined as follows. We take the process, which we, if you like, consider as a random selection of functions. We take the square of this process, and we integrate this function, which is then a measurable function, with respect to the time variable from 0 to infinity, against the Stochastic integral, which is computed against the Stochastic measure induced from the non-increasing bracket process of the process M. And this time integral then, which is a random quantity, it depends on the realization of the x trajectory and on the realization of the m trajectory. This quantity, which, let me say it again, is the total time integral of the square of the process integrated against the Stochastic integral of the increasing bracket process of m. This, as a random variable of that, we take the expectation. This is what we understand as the norm squared of the x process in the L2 space on omega times r plus, which is equipped with a measure, which is the Stieltjes measure effectively obtained from the increasing bracket process of M. So that's the space of processes which we will be able to define a proper integral of x against M. Okay, so L2 of M is then in fact this space which we have just introduced, is in fact just the conventional L2 space on this product space of non-negative time times the probability space omega if we equip this product space with the following measure, namely if we have a subset of this, if you like, of this Cartesian product, which is time against omega. So if we have a subset gamma of this Cartesian product, then this measure is defined as the expectation of the indicator function of this subset when we integrate this first with respect to the, again, Stieltjes measure induced from the pathwise non-decreasing bracket process of M, and that is then, so we take the total time integral of this and take as a second step the expectation of this. That is a measure on this product space, and if you familiarize yourself with this measure, you will understand that this X norm here, which we have defined, is nothing but the conventional L2 norm squared, in this case, for a measurable function which is defined on this product space if we equip this product space with precisely this measure. So let me say it again. If we have a square integrable Martingale, then we can equip the product space of non-negative time and omega with a measure which is effectively, and that's the key point here, which is obtained by taking the Stieltjes measure, the pathwise Stieltjes measure with respect to the non-decreasing process, with a non-decreasing bracket process, which is a continuous non-decreasing process and therefore of bounded variation, and take the expectation of that with respect to the omega variable. The L2 space of square integrable processes with respect to M is exactly this space. And before we finally introduce our abstract construction of the Ito stochastic integral, we need one final preparation, which is something like a Cauchy-Schwarz inequality for this bracket integral that we obtain if we take two square integrable martingales. Namely, let us take two integrators, so these M and N from this H space, or generally if we have a martingale from this H space, this will be a candidate for an integrator. And we take two integrands, namely a process X, which is square integral with respect to the process M, and we take a process Y, which is square integral with respect to the process Y, with respect to the process N. And then we might think of taking the pointwise product of the process X and Y, which is then, well, just again a measurable process, and we might want to take the Stieltjes measure, the full Stieltjes integral of this X times Y process against the bracket process, which is the covariation process of M and N. That seems to be like a reasonable object to introduce, and we, of course, we take the expectation of that. And we could ask ourselves, is this a bounded quantity in some sense, given the information that X and Y are each M and N square integrable, respectively? And in fact, we have an upper bound on the right-hand side, which looks pretty much like a Cauchy-Schwarz inequality, and it basically is a Cauchy-Schwarz inequality, which says that this product of these processes integrated against the covariation, that the result of this is bounded from above by the corresponding norms of the X and the Y process in their respective weighted L2 space. So this is just a very nice type of Cauchy-Schwarz inequality for these mixed Stieltjes integrals. Okay, in order to prove this, that will be an important ingredient. It's called the Kunita-Watanabe inequality. So if you like, it's like so it's a type of a Cauchy-Schwarz inequality for Stieltjes integrals, which in this stochastic context is called the Kunita-Watanabe inequality. Okay, we can prove this, for instance, by considering first these elementary piecewise constant in time processes xn and yn, of which we know that for general x and y, they approximate x and y for pointwise for all t and omega. So let us therefore reduce the argument to the case that we have these elementary processes which are piecewise constant in time. And by a further reduction, we can convince ourselves by just expanding these terms, we have linear combinations of such products, of such processes, that it basically is sufficient to consider the case when x and y are simple indicator functions of half-open intervals on the time interval on a joint time interval AB, and each of them then is multiplied with a certain random variable psi and eta, where psi and eta are both just random variables in the omega parameter. Okay, and then the expected value, which is appearing on the left-hand side of this claim, of this Kunita-Watanabe inequality, is then just because the x and y processes are constant in time, or piecewise constant in time, then this will be just the expectation of the product of x, psi, and eta times the difference of this bracket process, just by the definition, basically, of the Stieltjes integral on these two time points. Now, if we consider this difference of the Stieltjes if we consider the difference of the bracket covariation on these two time points by our polarization consideration, we can see that this is the limit in probability of these sums of products of increments, where we evaluate these increments on any finer and finer time grid, and these increments are evaluated at these ti points from this time grid, where in each point we take the inf with the upper time index b and the sup with the lower time index a. And this is done likewise here. Okay, so this difference of the covariation process at the two respective time points can then be obtained by these sums of products of increments if we take this discrete approximation on a finer and finer time grid. But this expression here is then now an expression to which we can apply the Cauchy-Schwarz inequality for sums, which allows us to derive just to bound this from above by the corresponding squares of these individual factors, sum taken to the raised to the power after the summation raised to the power 1/2, and here likewise for the end part. And we see by the same argument that the limit of these two individual expressions is just the increment of the bracket process for m alone when we evaluate at the time points b and a, and likewise the increment of the bracket process for n when evaluated on these two time points b and a. So that tells us that this, if we insert this into the expression that we had for this Stieltjes integral, expected value of the Stieltjes integral, where we had exactly this difference of the bracket process, we can bound this expected value from the product here by the expected value of the absolute values of the product of the absolute values of the psi and the eta variables, and then we insert the upper bound for this difference of covariations into we insert this upper bound by this difference in quadratic variation. And here I should probably say that sometimes for the bracket process of a martingale with itself or a stochastic process with itself, I sometimes use the shorthand notation to write a simple m, which is an abbreviation and which which probably seems to hide the fact that this is effectively a quadratic operation in M, but nevertheless. Okay, so this is then, as I just said, this quantity on the left-hand side is then bounded from above by this product, by this expectation of psi and eta, and then we have these differences of the bracket processes of M and N on these two time points B and A, and each of these differences is raised to the power a half. And now we can apply Cauchy-Schwarz inequality for these random variables which appear here. So we apply Cauchy-Schwarz to psi, where one factor is psi times the M increment, which gives a psi squared times bracket of M at B minus bracket of M at A raised to the power 2, but before we have 1/2, and the entire thing gets a 1/2 and the exterior of the expectation, and the same here. So this is just Cauchy-Schwarz inequality for the expectation operation, which was sitting here on the exterior. Okay, and here I see what I have left here is again just a plain Stochastic integral of the psi process, or the x process, if it is in this elementary form, squared against the bracket process of M. And let me see, so here's a misprint again. This is, of course, there's a 1/2 factor missing, and an exponent 1/2 missing. 1/2 here, and the same 1/2 here. So I see that inside this expectation, or the expectation is just the same as the conventional Stochastic integral. So this proves the claim of the Kunita-Watanabe inequality when the process x and y both are of this elementary piecewise constant in time form, and for, as I just said, for the general case of square integral x with respect to M and square integral y with respect to N. This claim follows from approximation. Well, and after all these preparations, finally we come to the main hero of the next lectures, which will basically the main object, and which will help us to develop even a much richer theory of stochastic processes as we had since now. And then we will now finally define in a proper mathematical fashion the stochastic integral with respect to in this case, square integral Martingale. So here it comes. Let omega Fp be a filtered probability space where Ft is a filtration which is indexed by the non-negative integers, and M be a square integral Martingale, which I should have said this much before, but I say it now and will probably say it a couple of times again, that whenever I'm talking about a Martingale here, unless I otherwise indicate, I understand a Martingale with continuous paths. So let M be a continuous square integral Martingale from this set curly H, and let X be a square integrable measurable process with respect to that square integral Martingale. Then there exists a unique process which we denote classically by X dot M, which will be the stochastic integral of X with respect to M in the end. Then there exists a unique process X dot M, which will be a square integrable Martingale with starting in 0, so it will be even in the subset of square integral Martingales which start in this 0, such that for any other square integrable Martingale, this new process, which has this symbol X dot M, when we evaluate this, when we take the bracket process, the co-bracket or the covariation of this new Martingale X dot M with any other test Martingale N, and we compute the bracket process of this, evaluate this at S, then this is given as the Stochastic integral of the X process when we apply when we take the pathwise Stochastic integral of this x process with respect to the bracket of m and n. So let me say it again. This is what is the claim. So we have a unique new martingale, square integral martingale, which has the symbol x dot m, and which we later will call the Ito integral of x with respect to m, which is a square integral martingale starting in 0, and which is, that's the claim, uniquely defined by being in H0 in this space, and by the fact that the bracket process with any other square integral martingale is given by this formula, which on the right hand side involves only quantities which we can understand, if you like, without any random knowledge, and it's just the pathwise Stochastic integral of the x process integrated against the Lebesgue-Stieltjes measure, which is induced from the bracket process of m and n. So that will be our stochastic integral, and moreover, the map which we effectively construct here, namely the map that takes a square integral with respect to m, square integral process x, and maps it into a square integral martingale. This process, or this map that takes the x process, the square integral integrand, and maps it into this new martingale, this is an isometry between these two Hilbert spaces. And this isometry is called this Ito isometry, and it will appear many times in the sequel. Okay, let me say it again. If we have a square integral martingale, and if we have a process x which is measurable and square integral with respect, in the proper sense, square integral with respect to that respect to that square integral martingale, then there's a unique square integral martingale, which is defined through a relation which refers to the bracket processes that we obtain when we take the bracket of this new to be constructed martingale with any other square integral martingale. And this bracket process evaluated at time s is then given as a Stochastic integral of that given x process with respect to this joint variation. So this new process x dot m is then and will be called the Ito stochastic integral of x with respect to m. And in the next session we will prove and give evidence why this is exactly the object that we were trying to construct. And we will connect this to our naive interpretation of what this integral should really be. And we will see that it is consistent with what we had desired to obtain. Okay, now let's prove this theorem before we make the connection to the actual, say, financial mathematics application or so. Let us first prove the claim that's made in this theorem. First, let us check that this process x dot m here is uniquely, if it exists, it's uniquely determined by this relation. So basically what it says is that if Z1 is one of those candidates, then this characterizing, or hopefully characterizing property star would basically say what this, if you look at it, it uniquely determines what the joint bracket with any other integrable square integral martingale is. And so if you have two such processes, Z1 and Z2, which stand on the left-hand side, then it says that the bracket process of this Z1, which is a candidate, the Z1 is a candidate, the Z2 is a process, then this inequality says that the bracket with any other square integral martingale of these two processes, Z1 and Z2, which are a candidate, they would need to be the same because they have the same right-hand side of this inequality, of this equality. So by linearity of the bracket, this in particular implies that the difference of the two processes, if we insert this and build the bracket with any other, is the zero process. And of course we can also take as the test process n here just the difference of Z1 and Z2, which tells us that the bracket of the difference processes is the zero process, and at the same time the process is as a difference of two martingales. It's a martingale. So the difference process would be a martingale with zero bracket, and it starts in zero, so it's just clearly the zero process, because the expectation of this thing would be the zero. So hence, the two processes must be the same, and therefore this relation star, which we have here, uniquely characterizes this process x dot m, if we can make sure it exists. Okay, for the existence of this process, recall that x is in L2 of m, is a square integral martingale with respect to m. And now we will make use of our Watanabe inequality. Namely, we introduce a linear functional, which is a linear map from this subspace of an Hilbert space of square integral martingales with start in zero, and this the linear functional that we want to construct, which has a parameter, if you like, so it will depend on the initially chosen process x. It will take an arbitrary square integral martingale with start in zero and map it onto the expectation of the Stochastic integral of the x process when we take the Stochastic measure with respect to the joint bracket of the m and the n process. N is here the argument, m is the fixed martingale, for which we want to construct the stochastic integral. So we take the full time integral of the x trajectory against the bracket process of m and n until infinity, and we take the expectation of that. So clearly this is a linear operation in the argument martingale n. And now we can apply the Watanabe inequality. And again, we have a little bit of a misprint. Namely, here you have the square, of course. So applying the Watanabe inequality, when this x is to be understood as a product of the one function with the x. So that then I get by Watanabe on the left-hand side x squared dms as the Stochastic integral and so forth, and there's a second factor in the Watanabe inequality. You get the 1 squared, which is 1 integrated against the bracket of the n process. Well, the left-hand side of these two, or the first factor of these two, is just my norm of the square integrable with respect to m process x. And on the right-hand side, well, I integrate the constant functions to 1 against the Stochastic measure, so that's just the same as evaluating this bracket process at infinity. But we had seen that this is another way to write the norm of this element n in the H0 space. So this is nothing but the norm of n in H0, which means that this functional, which we had just introduced, is in fact, as a function in n, is a linear continuous functional on this Hilbert space. And then by Ries' representation theorem, I know that there is a unique element in that Hilbert space that represents this functional. And this unique element I shall denote with this x dot m notation. So again, Ries' representation theorem tells me there is a unique element, whatever it might be, from this Hilbert space, such that this linear functional, which we had just introduced, which was continuous, can be represented as the inner product in this H space. And here the inner product with this H space I write with this double bracket in order to distinguish it from the bracket process in covariation. So I can represent this linear functional as an inner product of this unique element x dot m with the argument n. And if I recall what the inner product in this H space was, one way to represent this inner product in this H space is by writing it as the bracket between this new element x dot m and the n process. And I evaluate this bracket at infinity. and take the expectation of that. Okay, so I have this element x dot m, which is fine. And what I want to show now, of course, is that this element x dot m satisfies this inequality star. This equality star. So I want to show that x dot m with another element n has the right quadratic variation. So in order to do this, let me choose a bounded f stopping time, and let us consider for arbitrary n from this space H naught the product of this new element x dot m, which I have up to this moment just in abstract form. So the pointwise product of x and dot m, which is this new object, times n evaluated at tau. Okay, so that is what? So I can write this this expectation, if I want, also as the value, of course, of the n martingale at time tau times the x dot m martingale at time tau. But by closability of the process x dot m, I can also write this, so probably I should have an intermediate step. So this is the same as the, of course, x m tau process times n tau. I'm just writing it out. But this is the same as if I had taken just the expectation of the x m process at infinity given the sigma field f tau. N tau, that's just closability, and this is of course the same as if I write expectation of xm infinity times n tau given f tau, and this is just, if I forget, the conditional expectation, just the expectation of xm infinity n tau. Okay, so that was probably quick, but if you go through it, you will understand that basically by the Martingale property of this x dot m process, which is given for granted because we had said that this is an element from this square integrable Martingale space, I can write this this expectation of this pointwise product also as this, if I follow this computation, for instance. Okay. Now, instead of writing n tau for this evaluated Martingale evaluated time tau, I can also write this as the stop Martingale evaluated at time infinity. But the stop Martingale, of course, is also a square integrable Martingale. And so this inner product of these two Martingales at infinity is nothing but, again, the inner product in this H space or H naught space of these two elements, where here the stop Martingale n appeared. But since I know that x dot m is the representing element in H space, which represents this linear functional, I can replace this expression here also by the linear functional, which in this case has the argument n tau. N tau is the stopped version of the n Martingale. And then, for instance, by one of our previous lemmas, I know that the bracket of a stopped Martingale is the same as if I do the bracket and stop the bracket then. So this stopping time application, which acts on the Martingale here inside the bracket, can be taken outside the bracket. And I see that I have here now a Stochastic integral with respect to a bracket process, which is a stopped bracket process. But whenever I do a Stochastic integral with respect to a stopped function, remember that the stopped function starts or finishes or ceases to have any change in value after the stopping time. So therefore the increments will be 0 after the stopping time if I apply the stopping. And so therefore this Stochastic integral here with respect to a stopped integrator is just as good as if I do the Stochastic integral with respect to the unstopped integrator, but I do perform the Stochastic integration only until the stopping kicks in. So therefore I end up with this formula. So what have I learned from this computation? That the expectation of this pointwise product at any time, at any stopping time, is the same as the expectation of this Stochastic integral when the integration is carried out until the level tau. And if I just rearrange this equality to have a 0 on the right hand side, I see that the expectation of this pointwise product at time tau minus this integral in expectation is 0, which is the same of this if I had taken this tau to 0. That is true for all bounded stopping times. And if you recall one of our lemmas on the relation between optional stopping or optional sampling in Martingales, this tells me that this function here as a function of time has the same expected value independent of, so that this process as a process in time, of course, has the same expected value independent of where I evaluated, at what stopping time whatsoever I evaluated. Which means in the end that this process as a process of time is in fact the Martingale, and the term here on the right hand side here is a process of bounded variation which starts in 0. So therefore I have identified this right hand side here as the compensator, the uniquely determined compensator process, which is the unique process which starts in 0, which is continuous in a bounded variation, such that if I take the product of these two variables, of these two processes, of these martingales, and I subtract the right thing on the right hand side, then I get a martingale. So therefore, this process here is in fact the compensator. And this was exactly the claim of this equality star. This equality star tells exactly this, that the compensator between any n process of this space of square integrable martingales and this new element x is given by this Stochastic integral formula. So therefore, in fact, this new abstract element x dot m is the object that we were looking for, and it was obtained initially through an application of Ries's representation theorem in this space of square integrable martingales. And finally, we want to show the isometry claim. Okay, let's now not so complicated anymore. So we want to show that if we evaluate the norm square of this new abstract element x dot m in this H space, then we want to show that this is the same as the norm squared of the x process when it is understood as a square integrable process with respect to the Stochastic measure, if you like, of the process m, of this bracket process of the process m. Okay, so first of all, we see that this here is another instance of our equality star, because we have here, if we call this process on the right hand side in n, then we can just apply exactly our representation of this linear functional, which we introduced for the construction of this xm process. Namely, this bracket of these two quantities is given as the expectation of this is given as the stochastic integral of correction as the Stochastic integral of the x process with respect to the bracket which is obtained from the m and the n process. So therefore, this first step is just a repetition of this representing property of the process of the element x dot m for the linear functional L. And if we take a look at what we have here, inside again we have a Stochastic integral with respect to a bracket process. But we can iterate our previous understanding. We know we have just shown that the bracket process of this x dot m integral, or the x dot m object, with any other integral, with any other process, is given through this formula. So here, if you like, the we have a new n prime which we use here. That's now our n prime, and we know that let me write it like this. We had just shown that this bracket process here, which appears as the integrator inside this Stochastic integral, this is a bracket process again, and it's a bracket process which we can understand because it deals on the one of the two factors in this bracket process, the components, is again this abstract x dot n process, and we had just shown that this bracket is x times m times, if you like, this n prime. Where here's the n prime, but here n prime equals m, so therefore we have this formula, and we claim now. So sorry, what we have here, in fact, there is therefore a nested Stochastic integration operation, because we have here, we have on the outside, we have a Stochastic integral with respect to a process which is already a Stochastic integral. And I shall now use a lemma which is can be called the associativity rule for the Stochastic integration, which goes like follows. If you have two measurable functions and you have one right continuous function of bounded variation, and if you do a nested Stochastic integration as follows. So first you do an integral of the g process with respect to this bounded variation process, which is a new function of t now. And this new function, which is the first level Stochastic integration with respect to the h process, or h function, is a continuous function of bounded variation. So hence I could use this rho function again as an integrator for another Stochastic integration. And now the next time I do a Stochastic integration of the f function with respect to this new function which was obtained as a function as a result of the first order Stochastic integration. And then let me say it again, I just do another Stochastic integral, but now with this new bounded variation function. Then the claim is that this second order Stochastic integration is just as good as if I had taken just the product of the two integrands and had integrated this just one time in the Stochastic fashion against the integrator. So if we have a nested application of Stochastic integration, then it's just as good as taking the product of all the functions which were integrated at any time and integrate just once against the initial function of bounded variation. Okay, and this is now a situation which I have exactly here inside the expectation. I have a Stochastic integral here with respect to a Stochastic integral, and therefore this twofold Stochastic integral is just as good as the product of the of the integrands with respect to the integrator, which was appearing at the first level of the Stochastic integration. And I see that I have exactly, after I apply this and now actually do compute the outer expectation, I have here on the right hand side exactly the norm of this x process in this L2M space squared. So this proves, in fact, that this h norm squared of this new abstract element x dot m is the same as the L2 space, the square of the L2 norm of the x process of the integrand in this weighted L2 space with relative to the Martingale M, which finishes the proof, namely it establishes the claimed isometry. And this lemma which I have used here for pathwise iterated Stochastic integration, let me say it again, which says that nested Stochastic integrations are just as good as taking the products of all the integrands and integrated once with respect to the integrator. This is a not so complicated lemma from one-dimensional analysis, which I leave as a problem on one of the next problem sheets. And this is it for today. We have done quite a bit of material. We have cleared up the notion of a bracket process for a single martingale, or for a product, or for two martingales. We have established studied the space of square integral martingales, and basically using the Ries representation theorem, we have introduced an abstract map which maps a square integrable process with respect to a martingale into a new martingale. And its characteristic property is that we can identify the corresponding bracket processes, and if you look at the proofs once more, you see that all this is critically dependent on the fact that we were able to do analysis with the bracket process of a martingale or the joint bracket of two martingales. In the next session, I will explain, I hope in a convincing fashion, that this abstract process x dot m is exactly the object that we were looking for.